Accuracy can hide bad decisions. Decision curves show whether a model actually helps after costs and thresholds are included. This is the pattern you'll be able to implement by the end, which builds decision curves and chooses the model and threshold that maximize net benefit. I'm Professor Pi, teaching AI foundations with simple Python. In many applied projects, we do not just want the most accurate model. We want the model that actually improves decisions when acting has costs. Think medical screening, where treating someone has side effects and cost. Or fraud detection, where blocking a transaction annoys a customer. Success looks like a model that, when combined with an action threshold, increases net benefit versus doing nothing or treating everyone. Scikit-learn is a natural fit here because it produces the probabilities we need and gives tools to calibrate them. At the heart, a decision curve plots net benefit against a chosen risk threshold. Net benefit is a simple trade-off. It rewards true positives and penalizes false positives according to how costly a false alarm is compared to missing a case. Imagine you will act only if estimated risk passes a threshold. Decision curves show which model and which threshold give the best practical outcome. They also reveal when calibration matters. A model with a better AUC can still perform worse in decisions if its probabilities are biased. We will build a compact pipeline that trains two classifiers, computes net benefit across a grid of thresholds, calibrates probabilities, and then picks the model and threshold that beat a treat-all baseline. You will see how prevalence anchors interpretation and how calibration can change which threshold is optimal. The code is small and uses familiar scikit-learn components so you can reuse it on real data. Now, we'll create the toy dataset and baseline model. This snippet creates a small binary dataset and trains a baseline logistic regression classifier with scikit-learn to produce test set probabilities. The function makeClassification generates features and labels with a 30% positive rate, giving us an imbalanced but realistic toy problem. The call to train test split forms train and test partitions while preserving class balance. We fit logistic regression and then use predict proba to obtain calibrated-like risk scores on the test set. Finally, the variable prev holds the test prevalence, which anchors later decision analysis by showing how common positives are in this sample. The printed prevalence clarifies the baseline chance level your decisions must beat. Next, we'll compute net benefit at a single threshold to make the idea concrete. This example computes decision net benefit at a chosen risk threshold using the test probabilities from the baseline model. The function net benefit takes predicted probabilities p, true labels y, and a threshold pt, then turns scores into decisions with a simple comparison. It counts true positives and false positives, divides by the test size for rates, and applies the net benefit formula that weights false positives by pt over 1 minus pt. Setting pt to 0.2 reflects a willingness to act when the estimated risk exceeds 20%. Raising pt makes acting harder and penalizes false positives less. Lowering pt does the opposite. The printed net benefit shows the decision utility at this single operating point. Now, we'll compare two classifiers across many thresholds to build full decision curves. This code trains a scikit-learn RandomForestClassifier and compares its decision curve to logistic regression by scanning thresholds. After fitting the forest, the variable prf holds its test probabilities. The array TS lists candidate risk thresholds, and the list comprehensions compute net benefit for each threshold for both models using the earlier net benefit function. The calls to numpy argmax find where each model attains its peak net benefit. A compact conditional then selects the winning model, its best net benefit, and the corresponding threshold. Increasing N estimators can stabilize the forest's probabilities at the cost of time. The printed winner summarizes which model threshold pairing offers superior decision utility. Next, we'll calibrate probabilities and reevaluate the decision curve. This snippet uses scikit-learn's CalibratedClassifierCV to calibrate the random forest and reevaluate its decision curve. The object cal wraps the existing RF and applies isotonic regression with threefold cross-validation to correct probability miscalibration. After fitting, predict proba on cal yields new probabilities pcal for the test set. The list nbcal computes net benefit across the same TS grid, and ical locates the best threshold for the calibrated model. The variable gain measures the improvement over the uncalibrated forest at their respective optima. Isotonic usually helps when probabilities are too extreme. Sigmoid is smoother, but may undercorrect. The printed gain shows whether calibration meaningfully improved decisions. Now, we'll finalize by comparing to treat all and treat none baselines and pick the best strategy. This example finalizes selection by comparing the winning model to treat all and treat none baselines at the same threshold. The variable prev stores the observed test prevalence, which defines the treat all net benefit through the helper function nball. The list cans packages each model's best net benefit and its threshold from earlier scans. A generator and max call identify the overall winner and its operating point. The variable vsall computes how much the chosen strategy beats the treat all option. Treat none always has zero net benefit and is implicitly dominated if vsall is positive. The printed summary confirms a model threshold pair that improves real decisions. This toy build maps directly into a real system. Replace the generated data with your dataset. Use the same grid scan to find operating points that reflect management preferences. Log the chosen threshold and periodically recheck calibration as prevalence drifts. Recap: decision curves measure decision utility, not just accuracy. Use them when actions have asymmetric costs and you need an operating threshold. Caveat: net benefit depends on your chosen threshold grid and the reliability of predicted probabilities. Next step: tune the CalibratedClassifierCV spline by switching isotonic to sigmoid, or change the number of cross-validation folds to see how calibration affects net benefit. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.